similar to that of QVB. Very nice. So force acting on the current carrying wire will be I into L vector. If it is a curved wire, we will consider L vector as the vector joining initial to final position, and the theta will be angle with this vector and magnetic field that will be giving the magnetic force direction. So there are two methods of finding the direction. I mean, three methods in fact. The direction of finding the method of finding the direction. First is we can use the right hand rule, direction of magnetic force. So all the method that we use for the direction of magnetic field, because magnetic field is also given by the cross product. So the same formula we can use here also. If we use the right hand, using the right hand rule, curl your finger from the direction of current, which is a length vector. Current is not a vector, so that's why we use length vector, but ultimately the direction of that length vector is in the direction of magnetic field and in the direction of current. And if suppose there is a magnetic field towards right. So in this case, when we use the cross product from the first vector toward the second vector, you have to curl your hand. It is clockwise. For the clockwise curl, the thumb is pointing into the plane. Right. So for I, L cross V, L is upward, V is towards right. So when you curl your hand right side clockwise, the thumb is pointing into the plane. So in this case, force is into the plane. Okay, so right hand thumb rule is that you have right hand rule is you have to place your hand towards the first vector so that palm is facing the other. Okay, boss. Sorry, this was some call I had to pick. From the first vector to second vector, curl your right hand. Thumb is pointing into the plane. Into the plane. So current is. You understood this? How it is clockwise. If you curl clockwise, it is going into the plane. If you curl anti-clockwise, that will be out of the plane. So that was the first method. From the first vector L to second vector B, we need to curl our right hand. Second method is using the Fleming's left hand rule. I am not writing in detail because now you are not supposed to write a theoretical paper for the first term. Using Fleming's left hand rule, which is same as the one we did in moving charge, right? So if you apply in this particular scenario, when magnetic field is towards right, length vector is towards, so the current, the wire that we took in the example having a current, but obviously since your three fingers are perpendicular, so you have to place your index finger towards magnetic field, right? And then you have to place your middle finger towards up. So where is the thumb pointing? If you can try this with your hand, thumb will be pointing downwards into the plane. Thumb is going into the plane, so that means the force will be into the plane, right? Obviously at an angle theta, because all the three fingers are perpendicular, so we'll have to take that direction, which is perpendicular to magnetic field. Force will be into the plane. I don't have board right now, but I'll try to show it with my fingers with some of the examples. Yes. So third method, which is maybe quite easier to apply, that using the right hand palm. Because all these three methods we use to find the direction of magnetic field also. Stretch your right hand thumb in the direction of, such that your thumb is pointing towards the direction of current and fingers are stretched towards the magnetic field, then force will be perpendicular to palm in the direction of the slab, upward, the one that we use for the magnetic field direction. Using right hand palm rule, place your thumb in the direction of current, and your palm should be stretched in the direction of magnetic field, and then perpendicular, the fingers of right hand palm should be towards the magnetic field, and then it should be into the plane. So like in this case, current effectively is up, place your thumb in that direction, stretch your palm in the direction of magnetic field, then perpendicularly inward is the force. Force is acting into the plane. So the third one is quite easy to apply, but usually we have Fleming's left hand rule that will be asked or that will be used most of the time, but whichever way is convenient for you. Fleming's left hand rule is used for the direction of force, but most convenient is that right hand palm. Depending upon your so preference, you can use any of the three. So I'm just drawing some of the diagram. If you
So
can
can you
figure
move to
out.
the previous?
Yes, beta. I have not written the theory because we have done this also in the direction of magnetic field. Thumb along the current, stretch of finger towards the magnetic field, stretch of finger is towards the magnetic field, and perpendicular to palm outward. Perpendicular to palm outward is same as the direction of slab. Perpendicular to palm outward is the direction of force. Okay, so now we'll apply these three different methods for finding the direction of the magnetic force in the following cases. Magnetic field is into the plane and a current carrying wire has a current up. And first we'll take all the straight wires. All the wires are straight finite length wires. We have to just find the direction. Find the direction of magnetic force of the following wire as shown. You can use any of the three methods find the direction of magnetic force on the wire. Magnetic field is into the plane, current is going up from P to Q. What is the direction of force in this? Suzanne, what is the direction of force? You can use first left hand rule, suppose. Stretch your first three fingers together, and it should be in the direction of into the plane, right? The index finger should be into the plane. Rahul, Rahul, Rahul. I don't know is it visible or not. Can you see this screen?
Yes, sir.
Okay, so what is the force in this direction of force? Start with your first three fingers. It is going in. Magnetic field is going in, and then you have to turn your middle finger in the direction of current. Current is going upwards, so thumb will be pointing towards left. Thumb is pointing towards left, so force on this wire is towards left. Suppose if you use that right hand palm rule, thumb in the direction of current, finger should be stretched towards magnetic field. Magnetic field is going in, so the force will be towards left. Either you can use right hand palm or you can use the left hand rule. First, start with the index finger, magnetic field going on, then turn your middle finger in the direction of current, keeping the forefinger, index finger in the direction of field only. Thumb is pointing towards left, so force is towards the left direction.
So can you explain the curling of fingers again?
Come again, which?
The curling of fingers in the right hand thumb rule.
The left hand is clear.
Yes, sir.
Magnetic field is going in, thumb will be towards direction of current, finger is towards left. When you use right hand palm rule, in the right hand palm, we are supposed to use stretched palm, thumb in the direction of current. So current is going up, then turn your fingers in the direction of magnetic field. Magnetic field is going inside.
Yes, sir.
So your palm should be inside, and then give a slap. Slap is towards left. So that will be the direction of force. We use the same approach for finding the direction of magnetic field due to a wire. So basically, all these three methods are finding the direction of cross product. So whether you use left hand rule or use right hand rule or use right hand screw rule, they all are the method to find the cross product. You can use any one of them. This is specifically only for the force, magnetic field going in. Turn your middle finger in the direction of current, which is going up in this particular scenario. Thumb is towards left. If you prefer right hand should be, but in the exam they never ask right, use a right hand palm rule for finding the direction of current in the subjective paper. It was only define the Fleming's left hand rule. But for your convenience, you can use the stretch palm method. Thumb towards the current going up. Magnetic field is cross, so it is into the plane. So you have to place your palm into the plane and then perpendicular to the palm, which is towards the direction of slap. You will give a slap on the left direction, so force will be in the left direction. So I'm taking few more example. Now you have to try the one you will not be able to do. I will show it again on the screen. This is clear. Forces on the left in this situation. The first diagram, everyone. Bharat,
Yes, sir. Present.
You understood how we found the direction, why how it is left side?
Yes, sir. Using left hand rule.
Using left hand rule, magnitude will be BIL because all the three are perpendicular to each other, and this will be direction is towards the left. Second, let's say magnetic field is towards right, and the charged particle is going inside. The velocity of current is going inside, not the velocity. This is a wire which is going inside, current is going inside. What is the direction of force? Try using left hand or right hand, whichever.
So downwards.
Where?
Downwards.
Downwards?
Yes, sir.
Right. Aradhya, downwards?
So one.
Okay. Rahul, Isha,
So upwards.
upwards?
Downwards, sorry, downwards.
Downwards, yeah. It has to be downwards. Force should be downwards. You can use okay, so let me draw first few more, then all of them we will show, I'll show on the camera. Then suppose magnetic field is up and there is a current carrying wire in the form of semicircle loop carrying current from P to Q. Yes. So even into a semicircle, we have to make a length vector which is a straight wire. So accordingly, we will find the direction of magnetic field and magnitude of force. Magnetic field is coming out of the plane and a wire is having current towards left, suppose. Magnetic field is downwards and the wire has a current which is coming out of the plane. Length is L only, and in this third scenario, the radius is R. Figure out the direction and force. I'm just coming in 1 minute. Yes, try for all these four cases. Got it? What is the direction of force in the third case? What is the direction of force in the third scenario? So पहले तो हम L vector बनाएंगे P से QQ को join करने वाला, because the current is from P to Q, and this length vector will be 2R if R is the radius. So force wise, it will be B into I into length. Length is 2R. We'll not consider pi r as a length. We'll consider length as 2R because that is the length vector joining initial to final position. Right? What's the direction of force then?
So it's into the plane.
Into the plane.
Or is it out of the plane?
Out of the plane. And if it is up, current is towards right, so thumb is coming up, thumb is coming up. It will be out of the plane. Magnetic field is going up, magnetic field is going upwards, current or length vector is towards the right, so thumb is coming upwards, it will be upwards, out of the plane. Magnetic force will be out of the plane in the second scenario, and the magnitude will be Bi into L vector. L vector is not pi r, L vector is 2r. The vector joining initial to final position. Fourth one, what is the direction of force in the fourth one? Yes, direction of force.
So upwards.
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 Okay, right, upwards. Fine. किसी को doubt हो तो पूछ लेना. Here, upwards. Kanan. Kanan समझ आ रहा है? Direction is upward. What about fifth?
So to the right.
What's left?
Where?
Towards the left.
Fifth one, which direction is force? Towards right?
So towards right.
So I think
Towards
it's
right.
right.
The direction of force is towards right. B into I into L. The last two, here magnetic field is coming the sixth one. Sorry, fourth one. Magnetic field is up, coming out of the plane. Current is towards left, so thumb is going up. And in the fifth one, magnetic field is downwards. Current is upwards, like this. So thumb will be towards right. It will be towards right. In all this situation, we can use left hand rule or we can use right hand rule, whichever is convenient. Right hand is relatively much easier to apply. Like here, the current direction is towards outwards. Current is outwards, and place your thumb in the direction. Sorry, place your palm in the direction of current. Give a slap. Slap is towards right. So force is towards right. I hope understood. So this is the direction. Direction is the important one. Magnitude is BIL. Whatever be the shape of the wire, like in the question, the J, the question was asked, if a wire is in the form of sinusoidal curve and the equation of curve is given as y is equal to a sine pi x by L. So this is the shape of the wire from x equals to 0 to x equals to L to x equals to 2L. And there is a magnetic field B is equal to B naught K cap. This is X, this is Y. In a magnetic field, B is equal to B naught K cap. Find the force acting on the wire. So B naught K cap is out of the plane, Z axis is out of the plane perpendicularly. So there will be a force acting on it. Calculate the force on the wire, magnitude as well as direction. Though the wire is some curved wire, but we will use only the length vector, which is the vector joining initial to final position in the direction of current. So current I flows through it as shown. Join the initial to final vector. This is the vector which is 2L in length. So force to aa gaya. Whatever be the shape doesn't matter. Only initial and final position of wire you have to join. B into I into 2L. What's the direction? What's the direction? Downwards?
Downwards.
Downwards. Just a second. Yes, boss. Again, if I calculate the force on this wire PQR, which is placed in this perpendicular magnetic field. It is a wire which is in the shape of L, folded at an angle of 90 degrees from in between.
√2 IDL sin theta. No,
Why
√2.
sin theta?
No, there's no stress in sin theta.
Theta is already 90
It's
degrees.
already 90. Yes.
Yes. So we have to just calculate the length vector. Length vector become √2L, and it should be in the direction of current. So force will be B into I into L. Theta is 90 because magnetic field is into the plane and current is in the plane. So into sine 90. And what is the direction of force? Again, what's the direction of force? What's the direction of force?
Upwards.
Upwards. Right.
Yes, sir.
That force will be upwards. Right. So in the case of a uniform magnetic field, all these were the cases of uniform magnetic field. We can calculate the force on any shape of wire by using the length vector. So by chance, if it become a closed loop or a closed wire, what will happen? L vector will become 0. L vector will become 0 if it is a closed loop. For a closed loop, L vector will become 0. So that means the net force on that closed loop will also become 0. So if a closed loop of any shape, circle, rectangle, ellipse, if a closed loop carrying wire is placed in external uniform magnetic field, is placed in external uniform magnetic field, the net force on the loop must be 0 because L vector will be 0. Net force on the loop will be 0. And by this logic, that since it is a closed loop, every closed loop, the L vector will become 0 if it carries current and it is kept in a magnetic field. So since the length vector is 0, that means net force will be 0. As if is I into L cross B for any curved wire, it has to be the initial to final position value. But it is important that it must be in a uniform magnetic field. Only in uniform magnetic field, closed loop will have a 0 force. So let's take example of this. Suppose this is a metallic wire and it is kept in a perpendicular magnetic field. Net force is 0, that's fine. We understood mathematically since it has to be I into L cross B. But what happens to the size? Now the question is, if the current is passed in this loop, what happens to the size of loop? Will it increase, decrease, remain same? You understood the question?
Can you repeat?
It will increase, decrease, remain same. Yes. Yeah, it will increase. The size will increase, decrease, remain same, cannot predict. What's the answer? I know you said something I missed. What?
So no, I'm not sure what the question is.
You're not sure what the question is?
Yes, sir.
This is a loop which is placed some random shape.
Okay.
Now, when current is passed in this loop, we are saying that net force is 0.
Yes, sir.
Net force is 0.
Yes, sir.
Now the question is, what will happen to the size of this loop? Whether it increase or decrease or remain same when current is passed through it.
So should it remain the same?
Should remain the same. It should remain the same. Okay, let's try. Anyone else want to?
So by size, are you referring to the perimeter of the loop or the area covered by it?
Uh-huh.
So by size, are you referring to the perimeter of the loop or the area?
Perimeter cannot change. Obviously, the shape will
Yes,
change.
sir. So I think
The
it'll
magnetic
increase
wire.
then.
When there is a magnetic field into the plane, and we have kept some wire in an irregular shape, which carries a current maybe in clockwise direction. When the current is passed, net force is going to be zero because the L vector is zero. But if we consider any small portion of this wire, what will be the direction of force here?
So there will be no force, right?
What is the direction of force on this small length of the
Okay,
wire?
the small length. So it'll be outwards.
Where?
Wait, so it'll be diagonally towards the left.
It will be perpendicularly, I mean outwards, right?
Yes, sir.
What is the direction of force on this small length?
So it'll be diagonally towards northeast.
Again, it will be outwards. Any portion you take, the force will be acting outwards. So that means every part of this ring or wire, whatever it is stretched outwards. The net force is zero because every pair will get cancelled. Net force is zero, so it is a balanced force, but these forces on the different part of this wire will stretch it outwards, and as a result it will ultimately convert into a circular shape. Understood? Wire is kept in this magnetic field. It does not experience any force. That means the center of mass will not move. Center jahan pe tha, center will still be there. But the shape will change. Balance force can change the shape. Balanced forces can change the shape, that we have done in class 9th or 10th, whenever. Ultimately, it will convert into maximum possible stretching, and it will become a circular loop. Net force is still zero. So loop expands in size. अगर current अंदर की तरफ anti-clockwise होती, then it would have been contracted. Loop expands in size, but the net force is zero. Understood this? Why the size
Yes,
expanding?
sir.
Because of the force acting radially outwards from every part of this ring, the size will increase. Now another question that arises here, because it was relaxed, loose, the tension in the ring was zero. Now when it is stretched out, it is being pulled outwards. Now there will be a tension is developed in the ring, and we have to calculate that tension is developed. Why tension is developed? Because it becomes taut. When a string is pulled, it becomes taut. It will have a tension developed along the length that we need to find. Calculate the tension is developed in the wire due to stretching. And now we need to find that tension. Calculate tension in the ring. Fine. Radius R, radius is R. and we need to calculate the tension. अगर हम पूरे को as it is whole ले लेंगे तब तो tension हमेशा cancel out हो जाता है, जैसे किसी string में भी in a string tension always pulls, but every point there will be two tension, both are pulling each other. So as a result, as a whole, if we consider any string, then we won't be able to calculate tension. Tension calculate करने के लिए हम वहां से इसको cut करते हैं, and then we check that which force the tension is balancing or which acceleration it is providing, like that. Here also we'll do the same thing. Whole ring, if we consider, then you won't be able to calculate the tension. We will consider only some part of it, and let's say this portion is making an angle 2 theta at the center. We will separately consider this small portion of this ring which is balanced. Because the whole system is balanced, ultimately this small portion is also balanced. It is also not moving anywhere, not upward, not downward. So consider a small portion on the ring. थोड़ा zoom करके बना लेते हैं. So this is the portion that we are taking. What is the direction of tension? Tension is always along the length. और अगर zoom करेंगे तो वो इस cross section के perpendicular आएगा. This is the tension from here. बीच में जितनी होंगी वो pair wise they will cancel out each other. And magnetic field is into the plane. This total angle is 2 theta. Theta on the left side, theta on the right side. Since it is in a perpendicular magnetic field, it is in a perpendicular magnetic field. There will be a force on this wire carrying current. ये बहुत छोटा सा wire है, so length will be like a straight length. Just for this simply clarity, I have zoomed in. Force लगेगा किधर? What will be the direction of force? Outward. और ये जो magnetic force लग रहा है on this small part of the wire, it is balanced by the resultant of these two tension, because और तो कोई force है नहीं. When we considered the whole loop, then we said ऊपर वाला F नीचे वाला F से cancel out हो जाएगा. But now we are using only this small portion. So that small portion of this ring is balanced because the tension component. So theta, theta, 90 minus theta, theta. Similarly, theta, theta, 90 minus theta. Here it will become theta. Now, if you resolve the tension, t cos theta and t cos theta left side and right side cancel out, but their t sin theta will be added in the same direction. So this 2t sin theta acting in downward direction is balancing that magnetic force acting in vertically upward direction. 2t sin theta will be equal to right. Clear है ना? अब theta क्योंकि बहुत छोटा है, so we have considered a very small length, and it will be bi into l. Arc length is radius into angle. Theta is very small because we have considered a very small portion. And for a very small angle, sin theta को लिख लेते हैं theta. Both sides will become theta, 2 theta gone. Tension appearing in the ring when it becomes suddenly taut is B into I into R. Tension developed in the wire or in the ring because when it becomes taut. Rahul? Okay, right. Meher understood? Meher? Meher? No response? Oh, he is not here. Very nice. ठीक है, आगे बढ़ते हैं. Force on the wire, force on the current carrying loop. When net force is 0, that also means there will be stretching either outwards or inwards. It will have और आगे जब हम solid के साथ इसी को attach कर देते हैं, because of this force there will be some stress. That stress causes strain. The radius of the loop may change slightly. That is when we do 11th. 11 के साथ मिक्स अप करके ऐसे क्वेश्चंस बनते हैं फॉर द JEE लेवल. Find the increase in the radius of this ring if the Young's modulus of the wire is y. Okay, any shape of wire we can find. Now we'll take one case where it is non-uniform magnetic field. So calculate the force on the square loop placed as shown. Calculate the force on the square loop on the square loop as shown in the diagram. So there's a square loop of side length A that carries a current of small I, suppose. Side length is A and a distance of R. Find the force on the square loop. P, Q, R, S. Right. So though it is a closed loop, it is present in a magnetic field which is going into the plane. इस बड़े वाले infinity long wire की magnetic field होगी into the plane, but it is not a uniform magnetic field because the magnetic field magnitude will decrease. It depends also upon the distance from the wire. So the first wire PQ is on a different magnetic field. As we go, the magnetic field changes. RS is in a different magnetic field, though both are produced by the wire only, but because distance is different, magnetic field will be different. B1 is mu naught I by 2 pi R and B2 is mu naught I divided by 2 pi times R plus A. The magnetic field force due to the wire. Right? So बीच में जो ये वायर है QR और PS, इसमें क्या है? Any the same distance, let's say distance of x. अगर हम एक छोटा सा पार्ट लेते हैं, exactly same but opposite direction will be on the lower side और इन दोनों पे magnetic field की strength same होगी. Force will be equal and opposite. Any small pair on the wire QR and PS, those forces will be same because दोनों के लिए distance same है. So net force on these two wires, QR and PS. Net force on the wire, QR and PS will be 0. They cancel out. Obvious reason क्योंकि दोनों के लिए जो distance है wire से वो same है. X here and X on the lower side also. Distance same है तो magnetic field भी same होगी. DL is a length. Therefore, the forces cancel out each other. As a result, the net force will become 0. अब आते हैं केवल वायर PQ पे और वायर RS पे. Force on wire PQ. PQ पे करंट ऊपर की तरफ जा रही है, स्मॉल ही मैग्नेटिक फील्ड अंदर की तरफ है. So there will be a force. What will be the direction of force on this wire PQ? What will be the direction of force on wire PQ? PQ पे फोर्स कितना लगेगा? Yes. What is the direction of force in the wire PQ? मैग्नेटिक फील्ड अंदर है, so index finger अंदर की तरफ,
Towards the left.
middle finger so towards left F1 and that will be its magnetic current I. Magnetic field is produced by the bigger one, I, B1 into length is A sine 90. This is towards left or minus I cap, whatever. I is the current in this loop. B1 is magnetic field due to the infinitely long wire, mu naught I by R into A. Mu naught I small I divided A times 2 pi R. This is force due to wire 1, which is towards left. Now calculate force on wire RS. Direction of force on wire RS will be opposite. It will be outwards. Magnetic field is changed because of the change in magnitude, so force will also be not equal. It is opposite but not equal. So force on RS, F2 will be I into B2 into A times sine 90. Mu naught I divided by 2 pi times R plus A into A. This is towards right. So net force कितना आएगा? F1 and F2 are in opposite direction. बाकी vertical वाले दोनों cancel out हो गए. Net force on the loop is F1 minus F2. Mu naught capital I small I A divided by 2 pi R minus mu naught I small I A divided by 2 pi times R plus A. And this will be towards left, so it will be attractive force. Solve करोगे तो mu naught capital I small I LCM लेके आ जाएगा A square divided by 2 pi R into R plus A. It is net force, attractive force towards the wire. So this is a closed loop. It is placed in external magnetic field, but still net force is not zero. Why? Because it is not in a uniform magnetic field. It is in a non-uniform magnetic field. Correct? Fine. बेटा समझ आ रहा है?
Yes, sir.
सन्नाटा सा रहता है यार इस बैच में. Aradhya understood?
Yes, sir.
Very nice. ठीक है. Next is force between two parallel infinitely long wire. Force between two parallel infinitely long wires. Two infinitely long wires carrying current I1 and I2 kept a distance of R from each other. Distance between them is R, and we need to find the force. Why there will be force? Because one wire produces magnetic field at the place of second wire, and second will produce magnetic field at the first wire. Right? Okay. Magnetic field on the second wire produced by wire 1. Magnetic field due to wire 1 at the place of wire 2. So wire 2 is present in the magnetic field of first wire. It is into the plane. which is B1, and it's present in the magnetic field of first wire. Right, so second wire is in the magnetic field of first. Magnetic field is, because of the first wire, it will be mu
You
naught
not I1 upon 2 pi r.
I1 by 2 pi r, and direction is into the plane. What is the direction of force on this wire then? Wire 2. I into B into L into sine theta. The direction of force on the wire 2. Use the left hand, find the direction of force.
So towards left.
Second wire produces magnetic field on the first wire, which is out of the plane. I2 mu naught I1 by 2 pi r times L. But since it is an infinitely long wire, so L is infinite. That's why we measure the force acting per unit length. Force acting on per unit length is mu naught I1 I2 divided by 2 pi r. Two parallel wire, they exert force on each other, which is per unit length mu naught I1 I2 by 2 pi r. By similar method, force on wire 1 will be because of the magnetic field of wire 2. And again, force per unit length will be same, mu naught I1 I2 divided by 2 pi r. So two infinity long wire, iska force bhi दूसरी तरफ होगा. When two infinity long wire carries current in the same direction, they attract each other with a force of mu naught by 2 pi I1 I2 by r per unit length. So it is Newton per meter. It's not the Newton. It's force acting on a unit length of wire. Two four wire carrying current in same direction always attract. And if the current have been in opposite direction, these two wires will repel each other. Attraction and repulsion. The standard definition of 1 ampere, because current is a fundamental quantity, is also given by the same formula only. The current which on passing in two parallel wires kept at a distance of 1 meter exert force of 2 into 10 raised to power minus 7 Newton per meter. So current दोनों में same है. If that current is 1 ampere and distance between the wire is 1 meter, then force acting per unit length, if that force is 2 into 10 raised to power minus 7, because I1, I2 is 1, distance is 1, so it becomes mu naught by 2 pi, and which is 2 into 10 to the power minus 7 Newton per meter. So the current which on passing in two parallel wires produce a force of 2 into 10 raised to power minus 7 Newton per meter when placed at a distance of 1 meter is defined as 1 ampere. इसमें जरूरी नहीं कि हमेशा ये इनफाइनाइटली लॉन्ग ही हो. जैसे एक इनफाइनाइट लॉन्ग है I1, the another small length wire I2. This wire is floating. This wire seems to be floating because इसकी जो मैग्नेटिक फील्ड का फोर्स रहेगा ऊपर की तरफ और वो उसके वेट को बैलेंस कर लेता है. उसके लिए फोर्स पर यूनिट लेंथ मल्टीप्लाई बाय दिस लेंथ से कर देंगे. फोर्स ऑन अ यूनिट लेंथ. I1 is infinite, I2 is not infinitely large. Second wire is an equilibrium. तो उस पर जो फोर्स लग रहा है ऊपर की तरफ वो उसके वेट को बैलेंस कर लेगा. Because the current is opposite direction, they will repel. फोर्स हमने अभी निकाला था, that was per unit length mu naught I1 I2 upon R. इसमें L से मल्टीप्लाई कर देंगे, that will be equal to F. Right. Another conceptual question is that if in a spring current is passed, what happens to the size of a spring? Increases, decreases, remains same. If current is passed in a spring, what happens to the size? It compresses, it remains same, or it decreases, expands.
So does it compress?
What are now? On passing current through the spring, it gets compressed. So, because any two loop have current in same direction, clockwise in the first one, clockwise in the second one, and they will attract. Any two loops will always attract each other because they have current in the same direction, clockwise, clockwise both. So there will be attraction between any two such loop, and therefore it will attract, and due to attraction, so there is a contact. This is just a touch contact, it was not fixed. That contact will be broken when the current is passed. That was one experiment performed. The spring, if current is passed through it, due to the attraction between the coils. And why there is attraction? Because two like same direction current will always attract. So the contact is lost because of the spring gets compressed and that metallic contact breaks. Right. Okay, so we did a magnetic force on the current carrying wire and in the form of closed loop on any zigzag wire, electrode wire, we can directly calculate it with the help of I into L cross B. Next class, we will see magnetic dipole and current carrying loop, the total torque acting on the loop. Force is always 0, but there will be torque. So that we will do in the next class. Tomorrow's class we will solve questions based on these formulae of magnetic force and motion of charge. So please revise the formula, all these formula on the current carrying wire as well as the moving charge. In tomorrow's class we will be solving questions from DPPs on that. Okay, that's it for today. Thank you.
Thank you, sir.
Yeah. Bye-bye.